There is an object in the universe so violent, so extreme, so fundamentally broken by the rules of normal physics that light itself cannot escape it. Scientists spent 60 years insisting it could not exist. Then we photographed one. And the photograph did not just confirm what we expected, it quietly revealed something about the nature of time, gravity, and the fabric of space that most people walking around today have never heard. What you're about to learn is not a simplification, it is the real thing. And by the end of this, you will understand black holes better than most adults who have never sat down and actually thought it through. Let me start with something simple. Gravity. You already understand gravity. You have understood it your whole life, even if you never called it that. When you drop a sandwich off the counter, it falls down. When you jump, you come back. When you throw a ball, it arcs back to the ground instead of flying to the sky forever. Gravity is a pulling force that every object with mass exerts on every other object with mass. The more mass something has, the stronger its gravitational pull. A tiny marble pulls on you. You pull on it. The Earth, being vastly more massive than both of you, wins every argument. Now here is where it gets interesting. Because the question nobody asked for a long time was this: what happens when gravity wins so completely, so absolutely, that nothing, not you, not a marble, not even light traveling at the fastest speed in the entire universe can escape it? That question is where black holes were born. And the answer is stranger than anything a 5-year-old would expect, or a 50-year-old for that matter. Let me take you back to 1915. Albert Einstein, a man who looked like he had been personally victimized by a pillow fight, was finishing his general theory of relativity. Einstein had already changed physics once with special relativity, but general relativity was something else entirely. It was not just a new idea about physics, it was a new idea about what space and time actually are. Before Einstein, space was basically a stage, an empty backdrop against which things moved around and bumped into each other. Einstein said that was wrong. Space is not a backdrop. Space is a fabric, and mass bends it. The classic way to visualize this is to imagine a stretched rubber sheet. You place a heavy bowling ball in the center. The sheet dips. It curves around the ball. Now you roll a marble across the sheet, and instead of going in a straight line, it curves toward the bowling ball, spiraling inward. That curve is what we experience as gravity. It is not a force being pulled across empty space like a magnet pulling a paperclip. It is the shape of space itself, guiding things toward mass. Einstein called this geometry. The rest of the world called it mind-bending and slowly backed away. But here's the thing. The equations Einstein wrote down in 1915 were so powerful, so precise, that they immediately started predicting things Einstein himself did not believe. Within months of publishing the theory, a German physicist named Karl Schwarzschild, who was impressively doing this math while sitting in a trench during the First World War, solved Einstein's equations and found something alarming. The math described a point at which gravity became infinite, a point where the fabric of space curved so sharply, so completely, that it folded in on itself, a point of no return, a mathematical singularity. Einstein read Schwarzschild's solution and essentially said that is a very elegant piece of math and also completely physically impossible. He believed the universe would find some way to prevent such a thing from actually forming. He wrote papers arguing against it. He called it an unphysical result. He was, in this particular case, wrong. I want to pause here because there's something almost poetic about the most famous physicist of all time spending years arguing that his own equations were lying to him. The equations were not lying. Einstein just was not ready to believe what they were saying. Now, I need to tell you about a woman named Jocelyn Bell Burnell, because her story is going to matter in a few minutes in a way that connects everything. In 1967, Burnell was a 24-year-old PhD student at Cambridge. She had helped build a radio telescope the size of 57 tennis courts, strung together with wooden poles and wire, and she was the one analyzing the data that came out of it, not her supervisor, not the senior researchers, her. She was doing the tedious, painstaking work of scrolling through miles of paper printout, looking for signals from space. And she found something. A pulse. A perfectly regular, impossibly precise pulse, coming from a fixed point in the sky, so precise that her team initially called the source LGM-1. LGM stood for Little Green Men. They genuinely considered the possibility they had detected an alien civilization because nothing natural was supposed to be able to emit a signal that clean, that regular, every 1.3 seconds, like a cosmic metronome. What Bernal had actually discovered was a pulsar, the rapidly spinning, collapsed remnant of a dead star, a neutron star, a stepping stone between a regular star and a black hole. She had found the universe's warning shot. Keep that in mind, because I am coming back to it. Let me get back to the mechanics of what a black hole actually is, because this is the part most explanations rush through and most people walk away confused. A black hole is not a hole. It is not empty. It is not a vacuum cleaner in space that roams around swallowing things. It is an object, an extraordinarily dense, extraordinarily massive object. The densest thing that physics permits to exist. Here is how one forms. You start with a massive star. Not our sun. Our sun is not big enough for this, and I say that with affection. You need a star that is at least 8 to 10 times more massive than the sun. These stars burn through their nuclear fuel faster than smaller stars. Because they are so massive, their cores are under such extreme pressure and temperature that they consume hydrogen at a ferocious rate. When a sufficiently massive star runs out of fuel, the nuclear reactions that have been providing outward pressure against gravity suddenly stop. The entire star collapses inward in less than a second. The outer layers bounce off the incredibly dense core and explode outward in what we call a supernova, one of the most energetic events in the known universe, briefly outshining an entire galaxy of hundreds of billions of stars. And the core that gets left behind, if it is massive enough, keeps collapsing. It does not stop. It cannot stop. Gravity wins so completely that the matter gets crushed past the point where even atoms can hold their structure. It collapses down to what we call a singularity, a point of effectively infinite density, infinitely small, where the laws of physics as we currently know them simply stop working. The math produces infinity, and infinity in physics usually means we have hit the edge of our understanding. Around this singularity sits the event horizon. And this is the most important concept in the entire black hole story, so stay with me. The event horizon is not a wall. It is not a surface you could touch. It is a boundary. Specifically, it is the boundary at which the escape velocity, the speed you would need to travel to escape the gravitational pull, equals the speed of light. Inside the event horizon, you would need to travel faster than light to escape. And nothing travels faster than light, so nothing escapes. Not matter, not energy, not information, not light. The interior of a black hole is, in the most literal sense of the word, the most isolated place in the universe. Now, here is the pattern interrupt I promised you. If you cross the event horizon, you would not feel it. There is no wall, there is no alarm, there is no sign that says welcome. You are now in the part of the universe you cannot leave. If the black hole were large enough, you could cross the event horizon without any immediate dramatic effect at all. The tidal forces, the difference in gravitational pull between your head and your feet, would be small enough at a large black hole's event horizon that you might not notice anything unusual for a while. You would just be inside. And then gradually, inevitably, you would be pulled toward the singularity, and the tidal forces would grow stronger, and eventually you would be stretched out lengthwise and compressed laterally in a process physicists actually call spaghettification. They named it spaghettification. With a straight face, science is great. But here is where black holes stop being a weird physics curiosity and start being something genuinely profound. Because black holes do not just bend space, they bend time. I need you to hold this idea carefully because it sounds like science fiction and it is not. Einstein's equations showed that the more intense the gravitational field, the slower time moves. This has been measured. We have tested it with atomic clocks, on satellites, on planes, on mountaintops versus sea level. Time genuinely runs slower in stronger gravitational fields. Not metaphorically slower. Physically, measurably, literally slower. A clock ticking near a black hole would tick slower relative to a clock far away. As you approached the event horizon, time from your perspective would seem normal. But from the perspective of someone watching you from far away, you would appear to slow down, redden, fade, and freeze, just at the edge of the horizon, never quite crossing it for what would appear to be an infinite amount of time. You would be frozen at the edge of eternity from their view. From your view, you would have crossed it in moments. Think about what that actually means. Two observers experiencing the same event and arriving at fundamentally different answers about when things happened. Both correct within their own frame of reference, neither wrong. Just existing in different flows of time. This is not poetry. This is the tested, verified, experimentally confirmed behavior of the universe we live in. Time is not a constant. It is a variable. And black holes make that undeniable. This is where most science teachers lose people, by the way, because the human brain was not built to intuitively grasp that time is flexible. We have one very strong intuition about time, and that intuition is that it just moves forward at the same rate for everyone always. That intuition is wrong. It has always been wrong. We just did not notice because the effects are tiny at the speeds and gravitational fields we normally deal with. Black holes are where that illusion finally breaks. Now let me tell you what is really inside a black hole. And I mean this in the most honest, scientifically accurate way I can manage. Nobody knows. The singularity at the center is where general relativity's predictions break down. The equations produce infinities. And in physics, when your equation produces infinity, it is the equation telling you that it does not apply here anymore. It is not a description of reality. It is a description of the edge of your framework. What actually happens at the singularity is one of the great unanswered questions in all of physics. And the attempt to answer it is where black holes collide with the other great theory of the universe, quantum mechanics. Quantum mechanics is the physics of the very small, the physics of particles, of atoms, of the behavior of energy at the tiniest scales. It is also spectacularly successful. Between quantum mechanics and general relativity, we can explain almost everything that happens in the universe. The problem is that these two theories hate each other. They are mathematically incompatible. General relativity describes a smooth, curved, continuous space-time. Quantum mechanics describes a grainy, probabilistic, fundamentally uncertain underlying reality. When you try to combine them, the math produces nonsense. And nowhere in the universe are both theories more desperately needed at the same time than at the singularity of a black hole, where you have matter crushed to an infinitely small point and an infinitely strong gravitational field in the same place simultaneously. It is the ultimate physics cage match with no referee and no agreed upon rules. I am going to come back to this because there is a twist in this story that Stephen Hawking introduced in 1974 that I have been saving for a specific reason, and we are almost there. But first, let me tell you about scale, because this is the part that rearranges your sense of proportion in ways that take a few days to fully process. The smallest black holes we know of are roughly the mass of several suns crushed into a sphere about 30 kilometers across, that is smaller than a major city. The mass of multiple suns, inside a ball 30 kilometers wide. But black holes do not stop there. In the centers of most large galaxies, including our own Milky Way, sit what we call supermassive black holes. These are not just big, they are cosmically, incomprehensibly enormous. The one at the center of our galaxy, called Sagittarius A star, has a mass of 4 million times the mass of our sun, 4 million suns worth of mass, compressed into a region of space smaller than our solar system. And Sagittarius A star is not even especially impressive by supermassive black hole standards. The one at the center of the galaxy, M87, which became extremely famous for a specific reason I will get to in a moment, has a mass of 6.5 billion times the mass of our sun. 6.5 billion solar masses. If you place it in the center of our solar system, its event horizon would extend past the orbit of Pluto. The entire solar system would be inside it. And here is the thing about that scale that I want you to sit with. Even with that mass, even with that gravitational pull, most things in the galaxy are nowhere near the event horizon. Black holes are not cosmic vacuum cleaners roaming the galaxy eating everything. If our sun were magically replaced with a black hole of the same mass, which would be terrible for us for unrelated reasons, primarily the whole darkness and cold situation, the Earth would continue orbiting it in exactly the same path, because the gravitational pull at Earth's distance would be identical. The danger of a black hole is not that it reaches out and grabs you from across the galaxy. The danger is getting close enough that escape becomes impossible. Now, back to Jocelyn Bell Burnell. She discovered pulsars. She identified the collapsed remnants of massive stars spinning hundreds of times per second, emitting precise beams of radio waves like a lighthouse from hell. The Nobel Prize in Physics for the discovery of pulsars was awarded in 1974. It went to her thesis supervisor and to another astronomer, not to Burnell. She was not included. She had built the telescope. She had analyzed the data. She had made the discovery, and she was not on the prize. She handled it with more grace than I would have. She went on to become one of the most respected physicists in the world, eventually receiving enormous recognition, including a $3 million special breakthrough prize in 2018, which she donated entirely to a scholarship fund for underrepresented students in physics. $3 million. She gave it all away. I am choosing to tell you her story, not just because it is important, but because of what pulsars represent in the black hole story. They are the proof that nature really does collapse stars into impossibly dense objects. Pulsars are neutron stars, and neutron stars are what you get when the collapsing stellar core is not quite massive enough to become a black hole. They are the universe's near misses, the runners-up. They showed us that the extreme endpoints of stellar collapse were not just theoretical. They were real. They were out there. They were spinning and blinking and pointing their radio beams at us like a very high-energy lighthouse saying, yes, matter can really do this. And if it can do this, it can do worse. The confirmation that black holes were real, truly, observationally, photographically real, came in two extraordinary moments. The first was September 14th, 2015. That morning, two detectors in the United States, part of an experiment called LIGO, detected a ripple in the fabric of space-time, a gravitational wave. A disturbance in the geometry of space itself, traveling at the speed of light, produced 1.3 billion light years away by two black holes spiraling into each other and merging. Two black holes, each roughly 30 times the mass of the sun, locked in a death spiral, accelerating, the final merger lasting a fraction of a second, releasing more energy than all the stars in the observable universe combined emit in that same fraction of a second. And we felt the ripple from 1.3 billion light years away. The entire distortion of space at the detector was smaller than 1/10,000th the diameter of a proton. We measured it. We detected a cosmic event that happened before complex life existed on Earth, encoded in a ripple of space-time smaller than an atomic nucleus. Yep, you heard that right. The second moment of confirmation was April 10th, 2019. The Event Horizon Telescope, not actually a single telescope, but a network of radio telescopes spread across the entire Earth, from Hawaii to Chile to the South Pole, all linked together to form a virtual telescope the size of our entire planet, released the first image ever taken of a black hole. It was the supermassive black hole at the center of M87, 55 million light years away. The image showed a bright ring of superheated gas glowing as it spiraled toward the event horizon, and at the center, a dark shadow. Not the singularity, we cannot see that. Not even the event horizon directly, but the shadow cast by the event horizon. The absence of light where the escape velocity exceeds the speed of light. A photograph of the dark heart of a monster, 6.5 billion times the mass of our sun. The photograph was blurry by the standards of your smartphone camera. It looked like a fuzzy orange ring around a dark circle. and it was one of the most important images ever produced in human history. The scientist who coordinated much of the imaging algorithm work for that photograph was a 30-year-old computer scientist named Katie Booman. She had developed an algorithm called CHIRP to help reconstruct the image from the telescope data. When the image came through, a photograph of her reaction, hands over her face, expression of pure disbelief and joy became one of the most widely shared images of that year. A young woman seeing the shadow of a black hole for the first time. I find that moment genuinely moving, and I do not apologize for it. Now, the twist. The thing I have been building toward. The revelation that changes how you think about everything I have just told you. In 1974, Stephen Hawking was working on the intersection of quantum mechanics and black holes. Everybody assumed that black holes were permanent, that once you crossed the event horizon, your matter and energy and information were gone forever. The universe had swallowed them. But Hawking applied quantum field theory to the space just outside the event horizon and found something nobody expected. Empty space is not actually empty. At the quantum level, space is full of pairs of virtual particles, a particle and its antiparticle constantly popping into existence and annihilating each other almost instantly. This is experimentally confirmed. It sounds insane, and it happens constantly, everywhere, including right where you are sitting now. At the event horizon, sometimes one of these pairs appears with one particle just inside the horizon and one just outside. The one outside escapes into space. The one inside falls toward the singularity. The black hole loses a tiny bit of energy to the escaping particle. Over an extraordinarily long period of time, this process, Hawking radiation, as it is now called, causes the black hole to slowly lose mass and eventually evaporate entirely. Not in any time frame relevant to human civilization. A black hole, the mass of our sun, would take 10 to the power of 67 years to evaporate that way. The universe is currently around 13.8 billion years old. You would need to write the number 1 followed by 67 zeros to express the time scale we are talking about. But eventually, all the mass is gone. And here is the catastrophe, the information paradox. Because according to quantum mechanics, information cannot be destroyed. It can be scrambled, rearranged, transformed. But the underlying information about the state of every particle must be preserved somewhere. That is a foundational law of quantum mechanics. But if a black hole evaporates, and the Hawking radiation carries no information about what fell in, which is what the math seemed to suggest, then the information has been destroyed. Which would mean general relativity and quantum mechanics are not just incompatible in their math. They are fundamentally at war over the nature of reality. One of them is more deeply wrong than we thought. Hawking himself spent decades on this problem. At one point, he had a famous bet with physicists Kip Thorne and John Preskill over whether information was destroyed in black holes. In 2004, Hawking conceded the bet, announcing he had found a mechanism by which information could leak back out in the Hawking radiation, encoded in subtle correlations. Thorne refused to concede. The argument is technically still active among physicists. We do not have a complete answer. The universe is holding out on us. The information paradox is not just an abstract debate. It is telling us something about the deepest structure of physical reality. If information is preserved, it means the interior of a black hole must somehow encode and return information to the exterior, which changes everything about what the event horizon actually is. One idea, called the holographic principle, suggests that all the information inside a black hole is actually encoded on the two-dimensional surface of the event horizon, the way a hologram encodes a three-dimensional image on a flat surface. If that idea is correct, then the interior of a black hole may not be a separate volume of three-dimensional space at all. And there is a more provocative version of the holographic principle, one that some physicists take seriously, which suggests that the entire universe could function the same way. That everything we experience as three-dimensional reality could be a kind of holographic projection of information encoded on a two-dimensional boundary surface somewhere. That our universe, with its stars and planets and cups of coffee, and inexplicably popular television programs, could itself be a kind of cosmic hologram. I am not telling you this is true. I am telling you, this is what the math keeps pointing toward, and we do not yet have the tools to confirm or rule it out. The black hole is not just an object. It is a window into the parts of physics we do not understand yet. And the parts we do not understand yet are the parts that will define the next century of science. Let me bring this back to something concrete. Right now, at this moment, there's a supermassive black hole, 4 million times the mass of our sun, sitting at the center of our galaxy, 26,000 light years away. Stars near it orbit at millions of kilometers per hour. Space within a few light hours of it is warped so severely that general relativistic effects are measurable and significant. We have tracked those stars for decades, watched them swing around the invisible mass at the center in tight elliptical orbits, and confirmed that the mass producing those orbits is concentrated into a region smaller than our solar system. We have since imaged Sagittarius A star as well, a feat that was actually harder than imaging M87's black hole, because our galactic center is obscured by clouds of gas and dust, and because the material around Sagittarius A star moves so quickly that the image flickered like a candle in wind during the observation. But we got it. In 2022, the Event Horizon Telescope collaboration released the image. Here is the thought I want to leave you with. We started with a child's intuition about a ball falling to the ground. That intuition, followed patiently and mathematically for a century, led us to photographing an object where the laws of physics stop working, where time effectively stops at the boundary, where information may be encoded on a surface and projected as a volume, where space itself curves to a point of no return. The same intuition that explains why your coffee cools on the table also explains why nothing escapes the center of M87. It is the same force, just taken to its absolute extreme. Jocelyn Bell Burnell sat in a cramped observatory in 1967 looking at paper printouts, found something nobody was looking for, and proved that the universe was willing to go to extremes we had never seriously considered. She was not given the Nobel Prize. But the discovery she made led directly to the confirmation that collapsed stellar remnants were real, which led to the search for black holes, which led to LIGO, which led to the Event Horizon Telescope, which led to the photograph that made a young scientist cover her face with her hands in disbelief. You do not always get the credit, but the universe keeps the receipts. And here's the thing that has stayed with me since I started thinking about black holes seriously. The most extreme object in the known universe, the place where everything we understand about physics breaks down, the most violent and dramatic destination in all of space-time, it looks, in a photograph, like a blurry orange ring, like a cosmic donut made of the deaths of stars. The universe, it turns out, has an excellent sense of anticlimax. But inside that blurry ring is a darkness that bends time, holds light prisoner, and keeps a secret about the nature of reality that we have been trying to unlock for a century. We have photographed the shadow of the event horizon. We have felt the ripples of two black holes merging 1.3 billion light years away. We have mapped the orbits of stars around an invisible mass 4 million times the size of our sun at the center of our own galaxy. We have gotten that close, and we still cannot see what is inside.